this is mainly a kind of introduction to some basic concepts from machine learning. So it's kind of part of the first chapter of our book on algorithmic mathematics and machine learning. It's not so much about specific machine learning algorithms. It's not about deep learning. It's not about scientific machine learning. Scientific machine learning is a tutorial tomorrow with lots of deep learning approaches. I'm more about some underlying basic concept, which sometimes get a bit forgotten, so I don't have to worry about that, and explain some of the things which are working there. And then the last 20, 25 minutes are about some ideas, what people did, what we might want to do in combining machine learning and numerical simulation, and some concept of what we developed a couple of years ago, a taxonomy of informed machine learning. So what are ways and where to integrate domain knowledge into machine learning? So I think these are then the scientific aspects on that. And I highlight a couple of examples to see what one can do. So it's more like, I said, basic introduction to machine learning, so I understand some of the line concepts and terminologies and getting some ideas what people did, what one can do with machine learning in science and engineering. This direction. So kind of, and it's a bit more kind of classical 20 years ago point of view and not a kind of deep learning point of view or AI point of view. And as you see some of the terminologies, when I started in machine learning 25 years ago, it was called data mining. The big data aspect, or big data as a terminology came 10, 15 years later. I felt at that time fancy calling my PhD thesis machine learning and not data mining. But in the end, it's all kind of similar ideas, the same aspects. So, AI, however one wants to define it, our machine able to think like a human. But if to be intelligence, maybe from first it should be able to learn. So that's why machine learning, our machine is able to learn. And under the hood, in some sense, they all are based on ideas from statistical learning. So these are the concepts one needs to worry about to avoid pitfalls in interpreting results and not overestimating the prediction quality. The workflow is kind of a circle. So this is kind of first development for business analytics, but it works for any kind of approach. So we start with, okay, what is the problem, the task we actually are interested in? Worry about what kind of data do I have. Then the boring part and time-consuming part, doing actually data preparation. Then the fancy part, modeling, which everybody wants to do, and nobody wants to do data preparation. Then to evaluate, and then ideally actually deploy. But as you can see from the errors, everywhere it goes back. So you do some modeling, realize, okay, I need to do more data preparation because my model doesn't work. You do evaluation and see, okay, it doesn't work. Or the problem I actually want to solve, I can't solve, so I have to re-evaluate my business understanding, and you do it a couple of times. And actually, even after the deployment, you, in some sense, need to model observe what you're doing, because your model can get wrong over time, or the situation will change. So in some sense, you're never done. But these kind of circles, you see a couple of, one can find in different domains. I have another one for the statistical method, surprisingly only published in 2000 and not older. It's kind of, you have the same ideas, just with a different terminology. You have the problem, understanding modeling, you have the plan, measurement system, sampling design, data management, you have the data, collection, quality checks, you do the actual analysis, and you have the conclusion, and you start from scratch again. Or maybe not from scratch. But as you can see, if you look back, again, the steps are kind of similar, but and even data preparation and understanding also, of course, besides the data you have, you also have to vary which data can I get. Or after you do the modeling evaluation, you maybe have to worry about what is missing. My model isn't doing what it should do. Am I missing something in my data? And then at least in scientific areas, we at least have a chance to figure out, okay, maybe this property which we ignored is still relevant, or maybe we should put additional sensors measuring something. So this is all involved in that. In machine, one usually talks about 3 machine learning domains. The most common one, let's say, is supervised learning, so this prediction of properties. So in our sense, what we thought of as surrogate modeling of numerical simulation, it would be supervised learning. So I have some data points, coordinates, and a function value, and I want to learn this functional relation between x and y, and maybe worrying about some parameters or noise. Unsupervised learning is I only have the x, and I want to find structure in my x. So I don't have a label, I don't have a function value, but I want to see structure. For example, if I've done 50 simulations, I'm going to organize which simulation results are actually similar and which are different to understand what did change. And so they can talk about clustering, segmentation, or also compression would be also kind of unsupervised learning. And then there's reinforcement learning, which is, from the mathematics perspective, it's more like optimal control, but you don't know the model. So optimal control is kind of, I have a model of my state system. I know if I do this action, this is happening, and then I can optimize which action to take. And reinforcement learning, I maybe don't know the model. I maybe don't know the optimal reward function, what I want to optimize, and maybe have to learn. So this works by interaction with the environment. And then learn the model, and then do again the optimal control. And that's why, in some sense, they are related, because you have to learn the model, so it could be supervised learning involved in reinforcement learning as a subtask. So these things are related, and classically all 3 appear in machine learning conferences. A slightly different view to compare these 3, and adding another one, is if you worry about the quality of feedback from, let's say, the teacher. So start on the right-hand side, unsupervised learning, there's no feedback. I only have the data. I don't have any more information than my data. Reinforcement learning, I have a reward. So if I do an action, I have a reward feedback on quantifies in some way how good the action is. Supervised learning is, the examples are actually labeled by the teacher, so I know if it's a good or bad action. Here I only now have a quantitative reward. Here really I know this is a better one. And you can also, there's an area of active learning, which is the way where I not just have the data, but I also can say, okay, I want to have a label for this data point x, which I somehow select. And this means, given the x, I ask the teacher what's the label, what is the function value, what is the classification of that. So that means ask the teacher. These are different kind of quality of feedback in this learning procedure. So this is another way to think about that. And reinforcement learning, we might have heard reinforcement learning from human feedback, which is part of all these ChatGPT and LLM systems in their deployment. This, as I understand, is more like, it's not a direct reward which coming into play, but more a ranking. This response is better than this response, and from this ranking, then one can compute a reward. So this also plays a role in some other domains. Some classical and scientific examples to get a bit more feeling what's going on. So a classical image example is pedestrian recognition, which of course nowadays you would do with deep learning, but just to see that other things could have been done, is kind of I just use PCA or dimensionality reduction. PCA is essentially singular value decomposition of your data matrix. So the data are blurry pictures. So you see how old this data set is. It's very blurry pictures. And then you, no, sorry, that's not the blurry pictures. These are the actual eigenpedestrians and not the original data. So these are the first couple of principal components, and the later, the more noisy. And so you have the data matrix, you have PCA, singular value decomposition, and then you have structures in that and can do something maybe with that. So first, it's in a certain sense a dimensionality reduction, because based on this picture, you'd maybe go down to the first principal component, so you only have 10 features left, which are computed, and then maybe do stuff with that. But this is kind of a first step in data procedure, that you maybe reduce the number of features, or you subtract the noise, so you only worry about the signal, because the noise is often something you want to get rid of. And in numerical simulation, we know the same idea as proper orthogonal decomposition. So that's kind of, you have a bunch of numerical simulation results with the same resolution, and you do a singular value decomposition on that and get a surrogate model idea. One of the first examples where deep machine learning or deep learning neural networks were used in engineering to design something new, I found this example for firing new glass types. So they were after optimized composition of silicates to define the glass. And this is typically an engineering task. You have to try different things. And they develop a machine learning approach, so that they have some data sets which they already developed. They could build a machine learning model, and based on this machine learning model, they could estimate the properties thereafter, and then optimize over the machine learning model. And so they had this kind of, their key data was data they had from experiments, and could then apply this model to unknown composites and kind of look for new targets for glass. And then, of course, they need to first evaluate that and actually produce this glass. And the glass we have now on our cell phones, the so-called Gorilla Glass, was developed by the Corning company based on these ideas. So the classical data set is MNIST, handwritten digit recognition. So now we have a multi-class problem. So we want not only to recognize yes or no, we want to recognize these 9 or 10 different classes. And this is also kind of a historically machine learning approach, where this was used to automate the processing of letters, so that you could recognize the letters. And this is an example where if you don't have 99.5 correctness rates on this data set, you have a bad machine learning model, because in the end, it's relatively easy to do that once you understand what you need to do. And an unsupervised science example, which I forgot to update a bit more. So this is, since we talked about gene code, we can talk about genomics data maybe. So this is kind of the single cell measurements came from expensive experiments to very easily, systematically, in bulk, doable experiments in genomics. But then you have lots of data, high dimensional data, and you want to find a structure in that. So, so this is kind of what, in the end, they're after. So this is how stem cells, they start and they evolve into different branches over kind of the time in their lifetime. And so the measurements are done. So I'm starting, let's say, with blood culture and let it evolve in my kind of biological system. And after a day, 2 days, 5 days, 10 days, 20 days, I do the single cell experiment. So I have data. And then I want to find structures in that. And so this was kind of the hypothesis they had. And they could, based on dimensionality reduction, doesn't matter so much how they actually do that, but based on that, they could identify these branches. The color coding, of course, only came later. So at first, you have to look at that without the color coding. But you see that from the dimensionality reduction, it's possible kind of essentially to reproduce the structure. So this was the first idea, that you can reproduce what you know. And then they're using that nowadays. Lots of dimensionality reduction procedures are being used in single cell genomics to kind of organize this unlabeled data to find structures, branches, to understand more how things are evolving with cells. So this is why also unsupervised learning is important in science development. So to start the basis of supervised learning, so in the end, we are assuming there's some functional relationship between x and y. We don't know their age, so we approximate or represent this age by some model class, and we can do deep learning, we can do kernel-based approaches, we can linear regression, so HGB boost, so any kind of machine learning algorithm in the end can be used. But this is more the abstract level of, so that we have this functional relationship, and even there we have to include some noise, so that the functional relationship, since we have measurement noise, gives us this relation. And if the target value is a real number, we're talking about regression, and if the target value is -1, 1, if we talk about binary classification, or if we have 10 labels, we have multi-class classification. And sciences, I guess, we're more after regression to model functions, but it could be also that we maybe worry about classification, but I think the examples are more on the regression side. But the actual goal is not to replicate the data I have, because that's the data I have. The actual goal is prediction on new observations. And when can we do that? If the new observations kind of are similar to the old observation. Otherwise, there's no real hope to be able to predict something given of my training data. So the training data, my testing data should ideally be from the same random, or not ideally, should be from the same random distribution. And this is the key assumption, which one should never forget. That is the key assumption. So this out-of-sample prediction is kind of course, everybody wants to do that. Some people claim they can do that, but in the end, it's a difficult problem. And so in the end, we then have a way to measure. In statistical literature, we talk about risk, so that we're looking out of some function space, model class, and looking for this function, this model, which minimizes this risk. For example, here in the regression setting, least square error on that. And of course, we can write in an expectation, but of course, we have a limited amount of data, so we need to estimate that with finite limited training data, so we do some approximation in that. But so we approximate that by so-called empirical risk, which is sum over our data here for regression setting least square error, but we can do any kind of loss function, which gives some examples, classical examples in a minute. And so, of course, this gives additional error. So we have some error by going from H to H bar. We have some error to this empirical estimate. So we are already doing steps away from the original solution, and we have to worry about that generally. And even if we talk about this optimization here, if we do that, then, I mean, this is something we can optimize, but we shouldn't forget, what we're optimizing is not what we want to solve. So the optimization problem on the training data is just a surrogate optimization problem. In the end, we want to optimize our prediction quality, but we can't do that because we don't know where we want to predict. So even if we get this error small, it might not help us at all. So, which is different for other optimization problems we otherwise have, because the optimization problem is the problem we want to solve. Here, the optimization problem is just a tool, a step for identifying a model which solves our actual task of prediction. Typically, and mostly, least square errors are used, but you might want to use something else. So you can use, instead of the L2 error, you can use L1 error. In robust statistics, there's a so-called Hoover's loss, where you start with L2 and then go over to L1. Inspired from support vector machines, there's a so-called epsilon incentive loss, where you don't have a loss for a while, and then starting to penalize the error. So there are ways to do that differently, which means partly it means how strongly to penalize outliers. So the Hoover's loss is more robust to outliers, but maybe you don't want to do that. Maybe you also want to be affected by outliers. Or here you might say, okay, small deviation are not so important. So there's possibilities to do something different. The same in the classification setting. There it's more easy to see what effect is there. That's why I'm showing that. So to visualize that, so this is the actual ideal loss, the binary loss. Visualization, the x-axis is our actual target label times the function value. So if it's the sign is only important of f of x, so that's why this is a way to visualize that. So this is the actual binary loss, because that's not really something to optimize over. Probabilistic meaning is a logistic loss, which looks like that, which is also called cross entropy, and this is then also the way to generalize that to a more multi-classification problem, and the cross entropy is kind of the classical loss in deep learning methods. And there's the hinge loss, which has something to do with max margin and support vector machines, which come clearer in a minute. And this is to visualize all three, including the least square error. And this is also makes visually clear why we don't want to, you really want to use L2 error for classification problem, because we also penalize if we're overconfident, which we maybe don't want to do. But main thing is there are choices in your loss function one can think about, even classically. But in scientific machine learning or doing something more with kind of physics or chemistry, you can think about including in your loss properties of your problem. So physics-inspired, physics-informed loss functions, so that you add to your kind of label loss function some other loss functions which also measure something. So maybe not the target value, maybe something other properties, but we'll see that a bit more, or say a bit more later on that. That's the wrong direction. I have that now. Let's first go here. A classical problem is always overfitting and underfitting. So one can decompose what we're after. So this is the target, unknown one. This is a noise of the data. This is a model I have. One can decompose into the so-called bias variance decomposition. We have some data error, which is irreducible. We have the bias, so-called bias, which is kind of the error by the model, which by choosing our model class, we are in some way away from our target function, and the variance. So this is always happening. And of course, which error to get small, and this is a classical bias problem we have. So if I increase my model class, of course, the size and capacity of my model class, I get the bias error smaller because I have more richer function class. Classical one thinks about that in the ideal scenario, so one says the training sample error goes small. So if you have a small error on the training data, it doesn't tell you anything. So it's no problem to find a machine learning model with a small error on your training data. Essentially, if you memorize your training data, you have small zero prediction error on your training data, but that's not what you're after. And classical one observe that if I increase the model capacity, it goes down, but at some point the test data, the error on the test data goes up. So in the beginning with small models, if I have kind of a constant prediction, I have large error on my training data, on my test data. If I increase to linear or quadratic polynomials, I'm getting better, and at some point I'm getting worse. And of course, one never knows where that is, and one has to worry about how to find that. So this is a classical view. And deep learning developed the so-called double descent view. So in the modern regime, so again, we have the same picture before. This is a classical one. So we want to be. And then it was observed, actually, if I increase the model size even further, the test error gets small again. But that, in the end, one figured out why does it happen? Because you're changing kind of the setup, the regime. So this is kind of highlighted here. So here's the interpolation threshold. So at some point, you have interpolated all your data. So if you've interpolated your training data, then you really make large error on your test data. But if you over-parameterize, so have even more model size, more parameters in training data, you have to do something to pick from this large number of possible interpolation solutions, because you have over-parameterized, you have more than one potential model which fits your data, which to pick. And then you worry about smoothness, for examples. And so this is what's observed in deep neural networks, that there seems to be in the stochastic gradient descents, to quickly explain that, gradient descents we all know. I take the gradients of my loss and optimize my parameters. Stochastic gradient descents is if our loss function was the sum of the data points, which I can take the derivative on in view of my parameters of my function. Stochastic gradient descents means I have a certain number of data points. So batch stochastic gradient descent is a classical way to do it, standard way to do it. I have a number of data points. Only for these data points, I compute the loss, optimize, and take the next batch. And so the understanding is that in these optimization algorithms which are used in deep learning, there's some implicit regularization taking place. And if you further, once it kind of was showed that this happens, people realized, okay, it's actually, in some sense, also natural in other approaches. So if you take spline regression and over-parameterize, you would have the same double descent effect. But before, nobody really looked into that. But it still doesn't solve the problem that, where do I stop? That I need to worry about in these training procedures, what is a good kind of model size, what is a good estimation of my prediction quality on test data.
So there's a question. So if I'm sort of past the interpolation threshold,
and
I don't have any explicit regularization in my cost function,
I
would think that the cost function would be 0 across my entire data set. So then how do how do you keep learning after that point?
It's maybe not 0, but just small. But you're still changing your model. You're still optimizing. Especially in this deep learning procedure, you have layer after layer of something. So there's connections happening in. I don't want to talk too much about deep learning, but you have kind of layer of matrix vector multiplication by some nonlinear threshold, and so how the gradient passes through still kind of influences, still is doing something.
But it's still decaying exponentially as you get towards some minimum. So I thought that like the idea of the implicit regularization from SGD was usually in the initial phase when you're sort of like finding the right basin of attraction to go into. But you're saying this, it seems like also.
That's what they are saying. So I'm only can quote what I found on that, so I didn't work on that. But that's kind of the kind of speculation why this is taking place, so that there's something going on implicitly in this step. I mean, one can talk about regularization if you think about spline-based regression, if you have more spline functions than data points, which splines to take, then you really would worry about the L2 norm of the splines. So you have an active regularization, and that's the assumption.
That seems more clear,
Yeah, the assumption is there's something implicit happening, but it's not fully explained so far as I understood. But yeah, I mean, so it's a good question. One wonders if I'm actually almost zero, why still is something happening? But something is still. I mean, it's partly due in this. For example, if you take the batch view, I mean, you only have you never have all the data. In each update step, you only look at parts of the data, so you don't have the full picture.
But in the interpolating limit, all your residuals are zero for every data point. So it doesn't matter which batch you take, you'll still...
No, but it could be that the data you're getting, you haven't seen before. So let's take this is my bunch of data. I'm here. So the next batch of data I haven't seen before. So I'm not sure if I'm a zero for this data.
Well, I thought the assumption was that you're interpolating your entire data set. So if you bring in new data, then that gives you more information.
But in the practice, in the algorithm, what you're doing, you never see all the data. And you're updating on the net specs of data. So you might even deviate on the earlier data. So this idea that it's zero everywhere is in the algorithm, how they work, maybe not valid. I mean, this is a kind of theoretical aspect that once I'm after the interpolation threshold, but I think in the algorithm, how you're running that, you're never actually at the interpolation fully, because you only have incomplete information. I would think so, yeah. Other questions so far? And then maybe go back to this slide on regularization. This is the active regularization. So here we have this kind of, on this side, the points all the same, and here we should also have the points all on the same positions, and then one can vary about, this might be my original functions, so the green is the same, so which are different ways to choose. So the same function class, the same number of parameters, but I can introduce different smoothness constraints. So here I penalize strongly smoothness, and here I don't penalize so strongly, and the same here. So here I increase the smoothness constraint, and then I have different functions. But of course, one never knows upfront what is correct, so one has to estimate it some more. But this is kind of a thing what one kernel usually is building in, that I have enforced some smoothness. Or this can also be seen as kind of physics-informed constraints, so that I have, let's say, mass conversation, which I might want to build in somehow in my model, or my loss function. So I can add on top of my prediction measurement term, I can put regularization or other kind of properties which should be small. And there's another thing, particularly if you tackle a problem which is not tackled before. So you have kind of my estimation problem where I want to do machine learning on, and you don't have comparison results from others. You should also pick baselines, simple baselines. I mean, maybe even start the most simple spawn mean predictor and majority class predictor for classification and regression, which of course are useless. But so that you show, okay, what if I do something very naive, what comes out of that? And of course, if you're not better than that, then you're doing something wrong. Or even maybe a bit more meaningful is linear regression. So I fit a linear model. These are simple to compute, covering some linear effects between your x and y. And you should at least be able to beat that. Or for time series data, If you want to predict, have a time series, you want to predict the next time step, or the last time step. So here, then it's also my prediction. What is a good baseline is what if it does stay constant? Because you're more after the deviation from the constant, but if you're not better than the constant prediction, you're still not doing well. And this is from some studies we did, or experiments with master students or PhD students. We did something, and if you just look at the L2 error, you're not seeing this. So you need some baselines to really say, okay, this is actually useful. Or if you're kind of otherwise, I mean, if you're just more like tabular prediction, tabular data, so you have a couple of X data with not so much structure, want to predict some I value, you can use XGBoost, random forest, or there's now, since a couple of years, tabular foundation models. They just learned deep learning model on synthetic data, and so you can use this foundation models as a prediction model. For small means, I think, up to 50,000. So they're not for large-scale data, but for science application, 50,000 data may be already very much. So even if you think about doing some deep learning stuff, one can think about, okay, what other baselines are there to compare how good is what you're doing. Or if you also in the way, if I want to include some physics, some consistency, some aspects into that, saying, okay, I built my hand-engineered model because I know I built in the physics correctly. You should compare what's happening if you use a competitive model which doesn't use that. Because if your physics built in is not better than a classical approach, yeah, it's nice to have, but it's still maybe not the best way to go there. And I missed that to put it on the slide, but it's also good. Oh no, we can do that on the next one. And also measures more than one error. So we have the L2 error, which we put in the loss, but it doesn't hurt to always measure mean absolute error. This is called R value, coefficient of determination, or maybe maximum absolute error, because these tell you slightly different insights. And it might be that some model, if you compare different models, you maybe have similar least square error, but the one has a large max error than the other one. And so can you give your additional criteria which model is better, which model to pick? Or maybe you're actually after a small maximum error if you want to maybe use it for optimization purposes. You want to make sure that the max error is small. You have similar things for classification, true positives, true negatives. So the accuracy, how many the percentage which is correctly classified, true positives, true negatives, false positives, false negatives, sensitivity, specificity, and precision. But I think we don't need to worry about that right now. But what I wanted to mention is also if you have solving a physics-based problem where you have now some other properties than the label, it's worthwhile to measure these as well. So like a mass conversation, or if you know that certain values should be non-negative, maybe measure that. Because you might have a small mean squared error, but the physics properties might not well preserved. So one could think about building that into your loss as some constraint so that certain values should be above 0. But it could be that this constraints hinders the optimization procedures because on the way to the solution, it might want to be negative for a while, or it wants to be negative 10 to the minus 7, which you maybe don't need to worry about. So some constraints which may be physically meaningful might not be the right way to steer the optimization procedure. But that's also some recent example we had on gas network simulation where we saw, okay, we weren't really happy with the results, and we looked at further at some other properties we're interested in and saw there's some monotonicity not preserved. So how can we change the model that this monotonicity is preserved? So this can help you to understand the properties and improve your model. Then the ugly details, hyperparameter fitting. Any machine learning algorithm has some hyperparameters, which you need to fit in some way. So regularization parameters, so we have this regulation about smoothness, and you have a parameter in front of that, which tells you how strongly. So you have the error functional plus lambda plus smoothness constraint. And this you can tune, is it small or large? In deep learning, you have the number of optimization steps, so-called epochs, or you maybe stop early. Model design is also hyperparameters, how to build the model, how many layers I'm using, how large should the layers be. In kernel-based approaches, kernel to use. Essentially, the random seed and stochastic gradient is a hyperparameter. So this is all something you need to worry about. And they have a significant impact on the performance. So these you really need to work on to get this right. Ideally, you split your data into 3 sets. The training data set on which you actually do the training. The validation data set on which you, given trained model with a certain hyperparameters, you evaluate on the validation data sets. You do that for a couple of hyperparameter settings, and then you pick the best model, and this is then the model you want to use. And then to really estimate what you're really doing, you have a third data set on which you never look at. Ideally, you never look at the last third data set. Only do that once you have determined your hyperparameters, your model. And this is the actual prediction quality which can have. So you have training data set, test data set, where we have this bias variance decomposition into curves, and you have a third data set. And it's very easy to, let's just have a quick look at the test data performance, especially if you're in the model design phase. So almost always the results in a paper are better than they really are, because you might not have done that strictly. And even if you have small data sets, it's not, if you only have, let's say, 1,000 data points, you don't want to miss any data for your training. So there you need to do something different. It's called cross-validation. So let's say 10-fold cross-validation. I split my training data into 10 parts. I train on 9 and predict on the 10th, and takes the average over these 10 folds. And this gives me another way to estimate the performance. And here you do that for a couple of hyperparameter settings. So grid search, random search, quasi-Monte Carlo. There are some approaches which allow Bayesian kind of view on optimization. And for large-scale problems, of course, this becomes more difficult because if it's one run is costly, you don't want to do too many runs. So this is something which can be of a concern. You need kind of experience in which hyperparameters to choose. And for deep learning, one can see that also, since we have some randomness involved, the random steep, how we do this optimization, which data to use. And the result can heavily depend on the random seed as well. So keep everything constant, just have a different random seed, you get different results. So ideally, in the machine learning paper when you publish results, you should also kind of, I did 5 runs with 5 different random seeds, specified one, and what is the average result, standard variance, to see what's going on. And this can, so, I mean, some models, some approaches are a bit more better to cope with that. Some are quite worse. So I've seen results where it's an order of magnitude off depending on the random seed, which is, of course, problematic. Another aspect, so a bit different one. So this is motivated by the idea I have my data locations, and I now want to label this data. So far we had data, and the data all given. This is the idea I want to label the data only depending on the data locations. With the idea not every possible data location is a valid data point. So, for example, if you're after molecules, you can have features describing a molecule, smile strings or selfies. So these are, and you can generate descriptors from that, embed that in. So you have a certain feature vector which describes a molecule, but not every feature vector can describe a molecule. So not every point in your feature space is a valid molecule. And in principle, you have millions of potential molecules, and you want to label some of them. And so how to pick these ones. And this can play a role elsewhere as well. So this is to illustrate a bit what one can think about there. So the classical way, random sampling, would look like that. So we have these two dots where there's lots of data points. So these are kind of much more strongly used. You can talk about diversity. So you have a diverse subset. So it's again 100 points. But this is now optimized over covering the domain. So essentially, algorithmic-wise, one uses something like farthest point sampling. So adding the point farthest away from the data. And one can show that if I want to optimize the max error, this is advantage over this one. And one can try to balance these two, so kind of density-aware sampling, so that one kind of balances having good max error, good L2 error. But my point is there's a choice in the data set selection. Even if you're not worrying about active learning, which is maybe in view of Bayesian optimization, where you have the predictive task in mind and already a model, even if you're just building a database without worrying a model, so this is purely on the data locations, you have choices which data to label. And this can make, especially in the small data regime, 10,000, 20,000, 50,000, can make a factor of 2 difference in the prediction quality. It's not an order of magnitude difference, but a factor of 2 is already noticeable. So there's a choice in that. Other concern is covariate shift between train and test, or more like between train and where I actually want to deploy that. That's maybe the right way to approach it. So originally we assume always the data where we use is the same distribution as the training data. But in practice, there can be shifts. But at least we assume that the functional relationship between x and y is the same. So that and there are possibilities to take that into account to at least kind of improve the prediction quality on shifted data set to some degree. You can't fully resolve that, but there's possibilities on that. The basic idea is if this is my test data, this is my training data, this is my test data, I should kind of weigh this data, training data, which is close or overlaps with the test data strongly. So these have more importance. So it's a kind of importance weighting. Do that so that thereby the model is better near the test data. So this can help to some degree. There's also some kind of internal covariate shift happening in deep learning aspects. And while we're there, one should also think about concept drift. so that even the functional relationship might change, which particularly if what you're observing has some kind of time aspect, changes over time can happen, then of course this is something to worry about. So you still, in a deployed model, you have to kind of measure and monitor your model as it's still behaving as expected. And of course, and then final remark, there's a kind of transfer learning with every set, with one can say, oh yeah, this is different, so we do transfer learning and then it works, but doing transfer learning, of course, is not easy. So, so the idea is that I have theory-related problems and maybe I can benefit on my target domain by somehow using knowledge from my source domain, or the idea my target domain has only small data, my source domain has lots of data, so maybe I can benefit to some degree. But this is kind of a nice idea, but difficult to do really in practice. I mean, there's some ideas in deep learning where kind of where also called transfer learning, but where the prediction layer, which does the final prediction in the deep learning network, is kind of cut off, and something a new prediction is taking place. But that I would see as more the deep learning learns a feature representation and uses feature representations and for different tasks. So it's maybe something else than classical transfer learning. Okay. And we shouldn't forget things like concentration, of course, of dimensionality. So concentration of measure, basic idea. I have random samples in 100 dimensions. Randomly, I pick one data point, measure the distance of this data point, or Euclidean distance of this data point to all others, project it down to 2 dimensions. So that this one picked is in the center. And surprisingly, or maybe not surprisingly, all the other data points lie in a circle around that, which is, of course, a bit strange. If you think of so, all are similar distance away. So that means the Euclidean distance in high dimension is maybe not the best way to approach things. Or means that in high dimensions, we are not really covering the space equally. I mean, we are likely more on manifolds. So this is kind of the hope we're having, that we maybe can use other distances. We maybe have some manifold structure under the hood. And the same thing occurs of dimensionality. If we sample data points, have 10 data points in 1 dimension to sample. If we are in 100 dimensions, we need 10 to the power of 100, which we never be able to get. So in the same sense, even for to beat the course of dimensionality in data fitting is kind of the hope that it's some manifold on which we're living in. But of course, we have to kind of, it's not clear how we can find that. So there are lots of machine learning procedures, and I could do another slide just about artificial neural networks, Kolmogorov-Arnold networks, transformers, state space models, number models, whatever. And these are kind of linear regression problems, Kalman filters, projection pursuits, kernel neighbors, support vector machines. So well and so on that one. Any questions so far? So now switching a bit to some overview, some further step, and I should speed up a little bit. I'm going to come a little bit to informed machine learning, but first to have this flow components once more structure. So we have the problem, f, x, y. We have some data. The components of machine learning model are once more the training data, the model class, so which function class, which algorithm I'm using. The learning algorithm is the final hypothesis and then have the solution. And a bit later come back to kind of how to integrate prior knowledge. And as implicitly, we always integrate prior knowledge, because if we pick the training data, if we pick the features which features to use is already informed by our knowledge. So in some sense, informed machine learning is nothing new, but it was less systematically done before. Now to some further ideas to see how the loss function can influence the results. So this is kind of binary classification problem. So obviously, somewhere here should be the decision boundary. And this stems from the Ford vector machine. They have a separating plane, and they have a max margin idea, so that the margin around this line is maximized. And we see two other results. If I use the least square error, this would be the hyperplane, which of course misclassifies as one data point. And logistic regression would be this line. So slightly off on the max margin. But maybe it could actually be better because this minus looks a bit further away from that. So this might be an outlier. So it's maybe not even wrong to be further that. But of course, one never knows. So one has to measure that. And if one has something nonlinear, this linear separation doesn't work, but then there's a trick of going into higher dimensions, or transforming my data. So given my data, I might learn other features from my data, or in this view, I define the features. So I go from 2 dimensions to 3 dimensions, where the third dimension is s squared plus t squared. And then if I transform this data in 3 dimensions, then I can again linearly separate the hyperplane. So this is kind of the original motivation of the Ford vector machine, which was the machine learning procedure 25 years ago. But what I'm after is that we're still working after going into high dimensions or in a different feature representation. I still can work in the Euclidean geometry, so I'm still working with scalar products, and stuff is working, and still working with distances and similarities. So as soon as I have a scalar product on some features which I can maybe predefine, I can do something. And so let's go down here. So these are the feature maps. I have a scalar product. This implicitly defines the so-called kernel. And then I represent my function space. This kernel gives me a reproducing kernel Hilbert space. And the nice thing is that even with an infinite dimensional function space, if I have a finite amount of data, I have a unique solution by the so-called representer theorem. So in the number of amount of data, I can represent my function, which minimizing this loss here. So I have some, this is kind of the smoothness or the norm of this function space, my regularization parameters. This is some loss function. For classification, we have the hinge loss. And this is a way to do that. And what I'm after is that a lot of has to do with similarities. So scalar products, as soon as I have a scalar product, I can do something. In some way, always a scalar product under the hood is taking place. For example, if you look at deep learning models, there's a theory or view of neural tangent kernels, which has to do, roughly saying, as something how the evolution of the kernel of the neural networks during training takes place, can be viewed as can be interpreted as a kernel in a certain sense. So even there, this kernel scalar product view takes a role. And I think as was mentioned before, Gaussian process regression. It's the same thing to have it shortly here. So we have a smoothness constraint or Gaussian process prior in this Gaussian view. We have our least square error. We build a kernel matrix. We can solve it uniquely. And this gives us a way to estimate regression problems. And the nice thing of Gaussian process regression is it predicts our values, but it also predicts the uncertainty. So these are the data points we're having. And we can measure kind of, particularly in between, how large our uncertainty is. And this is for Gaussian process regression built in systematically and verifiable. So different topic, dimensionality reduction. That's why I stressed similarities just before. So as soon as we have similarities, we have also distances. And we can use distances and similarities for dimensionality reduction. So given similarities or distances of two data points and all pairwise similarities, I want to find embedding, low-dimensional representation, that with approximately that distances in the low-dimensional one are more or less the same than the original ones. And this is kind of the idea of multidimensional scaling, which is kind of a dual view of PCA. So one uses a covariance matrix, and multidimensional scaling uses a Gram matrix, so it's a matrix of scalar products. And you can convert scalar products to distances. And so as an example, we have here car distances of German cities, feeds it into this algorithm, and you need to tilt your head if you know the map of Germany, that kind of just based also on these pairwise distances, we can reconstruct where the cities are. And these are Hamburg, Berlin, Köln, Frankfurt, Munich, and which roughly fits. Or this we might know a bit better. We can do this for airline distances, so geodesic distances. So different distances still works. And we can do it in 2 and 3 dimensions. So the color coding, you can identify here as Europe. Of course, I mean, it's more, if I could rotate that, it would be more clearer that it does work. But just based on the geodesic distance, airline distances of cities, you can reconstruct the globe, so their locations on the globe. So here's Melbourne, here's Rio de Janeiro, here's Cape Town, and I guess here Europe and North America is a bit overlapped. But this does work. So this is kind of the funny, interesting thing. Just based on distances, you can reconstruct geometry. But then you want to develop what kind of distances. As we had before, the geodesic distance, Euclidean distance might not be the best one. So geodesic distances, if you can compute that or approximate that, you can use graph distances. You might use Wasserstein distances or optimal transpose, Earth mover distances, or some other one. Signature distance is kind of based on the signature transform. So you kind of do something with your path and can represent the past in a certain signature. For time series, there's something called dynamic time warping. Cosine similarities are particularly used in machine learning if you have back of words embeddings, representation, diffusion distances, something about diffusion maps. So there are several ways to represent distances. And there are some other approaches, UMAP and t-SNE, which are often used for dimensional reduction of visualization of embeddings. But these don't preserve distances. Only locally they try to do that, but globally they don't. And so one has to be very careful interpreting that. So we are very quickly try to interpret anything we see. And there's less structure here on that level in UMAP or t-SNE than for otherwise. And so this is kind of one thing to use about dimensional reduction. So we start with some vectors. We maybe do some clustering. So we look for groups. So we artificially create labels. So we look for structures there. We can do dimensionality reduction in 2 dimensions. So we visualize that. And the color coding is then computed by clustering. So clustering is then grouping things nearby, so a cluster is data which are close to the cluster center, and the nearest one and farther away to other cluster centers. And so this gives you a way to visualize, investigate your data maybe. And to example with simulation, so I have to do with car crash simulations and working on methods to analyze that. So each point here is one simulation result of a firewall in your car. And so we use methods to kind of organize 50 or 100 simulation in one picture to see kind of differences in their behavior. So that one has a bigger overview what kind of behavioral modes are there, or that we maybe can identify outliers, so a simulation which is really off from other ones. If it's good or bad that it's off is another question. Or that there are certainly behavioral modes, but this is based on this simulation result you can have to think about what is similarity of simulations. You can start with PCA, but that usually is not the best way, so we have used diffusion maps or our own procedure. In the same setting, what you also can do is, again, each point is one simulation, but now over time. So here we used not a dimensionality reduction, but a different feature representation. It's based on the Laplace spectrometry operator of the surface. So we use that as a spectral decomposition of the Laplace spectrometry operator, project our mesh function on the spectral decomposition, and visualize here the first three spectral coefficients. And the difference here for this part, so the structural beam in the bottom of your car, the difference was the plate thickness, so that we wouldn't see in the surface. So in the beginning, they have all the same position, and then over time they evolve, and here we have two behavioral modes. And there are ways to visualize the time behavior, how things are behaving similar or differently. So there are ways to see more. I mean, if you do a couple of numerical simulation, it could be interesting to see how they behave differently, especially if it's after designing something or optimizing something, or if you do some Pareto front optimization, you maybe want to look at the outputs of the simulation, which are on the Pareto front, to see what other structures are there. So this is further investigating what's happening there. Then we're coming back to that. So now about this prior knowledge. So there are several kind of source of knowledge which one can think about: scientific knowledge, world knowledge, expert knowledge, and talking about detail would be another tutorials. And you can represent, or it's being done, represent in several ways. So like algebraic equation, differential equation, simulation results, spatial invariance, logic rules, knowledge graphs, so like graph representation of connections, probabilistic relations, and human feedback. And then you can integrate that in all levels, as the training data, on the hypothesis set, so in the model architecture, in the learning algorithm, or check the final hypothesis. So there are several ways to integrate knowledge into your learning algorithm. And there's quite a bit of examples. The most common one, I guess, is the loss function, to have additional loss terms, or kind of certain basis function integrated. But there are more ways to do that. Knowledge graphs, kind of, if you think about large language models, you maybe heard about RAG approaches, which is kind of adding knowledge or systematic checks to what's in large language model outputs. And then you can think about knowledge graphs as a way to specify knowledge which a large language model in its output should reflect. And come to the end. Took a bit more than I thought. So now about combining machine learning and simulation. So we had a paper a couple of years ago on that in the model. So you can use that in both views. So you can use simulation in machine learning, or you can use machine learning in numerical simulation. The most classical way in machine learning is your simulations get training data, synthetic data. Common example is autonomous driving. They know lots of simulations of visual setups to generate additional training data for the autonomous driving setups. You can integrate that into the model. So certain, let's say, basis functions integrate in the model, which stand for numerical simulation. Or in the learning algorithms, that you have some constraints which are implicitly defined by numerical simulation. Or more importantly, you have an outcome of the machine learning model. Let's say you use machine learning to find a new molecule or and you can verify if this new molecule is reasonable by doing some numerical simulation on that. So you do this machine learning procedure, which is quicker, and in the end, you verify that the output is what you're after. And the other way around, machine learning assisted simulation. I forgot always what I want to say there. Yeah. So the classical one is in the model part, surrogate modeling. So replaces use machine learning as a way to build a cheaper model. You can think about input parameters in the sense of, let's say you have a numerical solver. Colleagues of mine did that they develop algebraic multigrid method or fast solver technologies. And based on kind of runs and their behavior, they now have a machine learning model to set up which solver to use with which parameters. So you learned kind of which solver settings to take. You can use it in the numerical methods. Like in multi-academic simulation, you need to evaluate potentials, and there you can use machine learning learned potentials, which are quicker to evaluate. So if you have a costly component in your finite element solver, which has additional kind of sources or knowledge, you might replace that. Or simulation results, what I just showed you, that we want to analyze the simulation output, either a couple of them, or even do machine learning on one output. So on all these, you can do something. And details you find in this paper. And one can think about how to integrate that more. So this is more vision that one can maybe think about learning simulation engines as in, I mean, we talk about surrogate models, which means we done a couple of simulations, but usually the simulation, when they run, they don't know that they're being used for a surrogate model. What I'm after is, if I do 50 similar simulations, I can take advantage of that I already run 1021, and maybe improve the last ones by certain parameter settings, reusing starting configurations so that it's overall, I mean, the simulation output should be the same, but it maybe can be done more efficiently. Or what I just said, I have solver settings, which I maybe can adapt based on the first 20 of my surrogate model data which I run and improve the later stages. And in the end, it's kind of, I mean, what multi-fidelity is about, that I vary about different model precisions, and with machine learning, you might be able to think about, okay, which model to use when, which prediction accuracy I need for which task, or even think about domain decomposition, that you separate your domain in different models, which in some areas you can use a surrogate model, in some areas you need a more specific model, and machine learning can maybe help you to realize that. And final topic is explainable machine learning. And it's not like explainable machine learning is well defined, so everybody means slightly different things by explainable machine learning. We have talked about 3 different aspects: transparency, interpretability, and explainability. Transparency is kind of that the model you're using is reasonably transparent. Interpretability is that you can interpret the outcome or visualize the outcome. And explainability is actually the human understandable part of that. So to explain what I'm after, so the interpretation, so this is a classical example. So you're doing heat maps, so it's a prediction model. Data sets classify what you see on this picture. And classical ways to so-called heat maps. And you see here is something highlighted. And if you look here, you see there's a watermark by the photographer. And almost all the horse pictures in this data sets came from this one photographer. So the machine learning model didn't pick up on the horse, but on the watermark. So the interpretation is this thing here. And the explanation is that it's a watermark. But the interpretation method doesn't tell me it's a watermark. That is, we as a human realize the interpretation tells me that the watermark is responsible. So this is the difference I'm after. And here finally, so even if you put it on the Porsche car, you get a horse picture. So this is, we think, important in scientific aspects to kind of, if you want to science discovery insights, you need to vary explainability and also scientific consistency. So if you have your outputs, you could, as I said before, you should think about additional properties you can check. So you have something in your loss function which you want to predict, but typically you have additional properties in your model which you can investigate to check if these are reasonable. And often, it can happen that L2 error is small, but what other properties are not well preserved. And what you can do, and let's go just here to not explain in details, and we can finish reasonably in time. So what we did here is we learned a predictive model for rain prediction on this area and on this area. And that's the one on this area, we then kind of drilled down to this area. We did a interpretation method, which kind of did some interpretation, doesn't matter what the specifics. So this is the original. And so we did this variant approach. We learned on a different size. But if these kind of interpretation of the relations were valid, then the size of the model where we learned on shouldn't matter. But here we realized on these areas we had a different interpretation or different sensitivity analysis. So this means that the model we learned here in these areas didn't learn something scientifically consistent, because if I learn in a larger size, something else comes out. So this could be a way to check the consistency of your model. So you slightly change your problem and check, is it still giving me the same kind of interpretation results? So it's kind of a debugging tool possibilities. And here, this is a similar thing where we kind of varied the location. So we slightly shifted the data and still got the same observations. And final slide, causal deep learning, which is in short, we learned causal relations, essentially learning the effect of the so-called do operator from Perl's causality theory. So you build a model, a structured graph model of how things influence each other. And you can approximate certain aspects of that by deep learning model. We could use that to investigate the impact of local soil moisture on local and regional precipitation. And so we learned this causal model, did some sensitivity analysis, and could get new scientific insights. So this is kind of not fully understood in geosciences. And based on that, we could realize that there's positive local and negative regional coupling, and the strongest coupling is in mountainous regions and ridges, so between soil moisture and precipitation. So there are ways to further analyze your data and build in all your knowledge, which is a causal graph you build, and investigate what you don't know in view of sciences. And that's all I wanted to say. Thanks for listening.